We're going to look at three examples of calculating with forces on moving charges. The first two are going to be pretty quick and easy, and the third one a little bit longer. Let's say we know the force acting on a particle moving at a certain speed, and we want to find the magnitude and direction of the field. To find the magnitude, we can just use F equals QVB, and we're given F. I guess we can rearrange this to solve for B first. So it's going to be F over QV. We plug in 8 times 10 to the negative 14th. The charge, this is a proton, so 1.6 times 10 to the negative 19th. And then we've got the velocity of 5 times 10 to the 6th. Throw all that in, and we get a 0.10 Tesla magnetic field. To figure out the direction, we can use our right-hand rule. We kind of have to reverse things a little bit. So the force, we need to point our thumb in the direction of the force and our fingers in the direction of the velocity. When we do that, our palm is going to point in the direction of the magnetic field. So the magnetic force would be inward, into the page or into the screen, whichever way you want to think about it. Moving on to number 2. We know that an electron is traveling at this speed in a magnetic field of this strength, and we want to describe its path. As we saw earlier, these particles will always follow circular paths because you have a centripetal force acting on them. And to describe it quantitatively, essentially what I want you to do is, or what we are going to do, is describe the radius of that circle. So one of the equations that we derived in the previous video was mv over qb. So again, we've got everything we need. Mass of a electron is a known quantity, and then we've got the velocity, 2 times 10 to the 7th. Charge on the electron is the same as it was before, or in the previous example, I mean, times 10 to the negative 19th, and a 0.01 Tesla magnetic field. Why put the unit on that and nothing else, I don't know. We end up with a radius of 0.011 meters as we go around the circle. One more example. Let's say we know the force as vector components, and then we also know the magnetic field, and we want to find the velocity. So this gets a little trickier. We know that F equals QV cross B, but it's quite a bit easier when you have V and B and you're finding F. If you're given F and you have to go back to find V, it takes a little bit more work, but I will show you, and now you'll know how to do it, and you'll take good notes, and everything will be fine. Essentially, we want to break this up into the components. So the force can be written in general as the x component in the I hat direction, and the y component in the j hat direction, and the z component in the k hat direction. Now this cross product thing here, the q just comes along for the ride, and then this is the determinant of the following matrix. So I, j, and k, the x, y, and z components of the velocity, and the magnetic field. So bx, by, bz. Alright, now if we think about which of these components are going to be 0, and we can kind of simplify things a little bit, we have an x and a y component for our force. So let's get rid of the z component, plus fy, j hat. And then for our magnetic field, we only have one of those components. The velocity is what we're trying to solve for, so we can't get rid of any of those components. I, j, k, and we've got 0, 0, and then we have the z component of the magnetic field. At this point, we can think about what's going on with this determinant. Only two terms will not be 0, the term going this way and then the term going that way, if you remember how those determinants work. So we'll go ahead and write that out, plus, and then that's going to give us q times vy bz in the I hat direction, minus, because you subtract the other terms in this determinant thing, minus q times vx times bz times j hat. And at this point we just set the components that are in the same direction equal to each other. So I'm going to jump over here just because there's more room. So we get fx equals q vy b, I guess bz. And then we can also get fy equals negative q vx bz. And then if we solve each of these equations, we can get a couple of the components of our velocity vector, which is what we're trying to find. And we get Vx is Fy. I'll put a negative up here, and there we go. From this point we can go ahead and plug in numbers. So we've got 3.8 times 10 to the negative 13th. That's an ugly Q there. Try to make it a little better. Do we know Q? Oh yes, it's an electron. So 1.6 times 10 to the negative 19th, and that is a negative charge. That's going to affect our direction, so be sure and put that in. In the previous one, was it an electron? Yeah, but we just were worried about the magnitude, so that's why I left it off there. Anyway, moving right along, and then we've got 0.85 for the magnetic field, so this works out to be negative 2.79 times 10 to the 6th meters per second. If we plug in numbers here, I'll spare you the agony of watching, but it works out to be 1.99. We got a negative there, we get another negative here, and then we also get a negative. Oh, we had a negative on our force as well. So we had 3 negatives, which is why this thing comes out negative. Alright, negative 1.99 times 10 to the 6th meters per second. And we can write this as one big happy velocity vector. I'll pull a negative out front, 1.99 in the I hat direction plus 2.79 in the j hat direction. All of that to the power of 6, 10 to the 6th meters per second. Now you notice we didn't figure out Vz. Our calculation does not imply necessarily that Vz is equal to 0. Essentially, we just don't know it. We got our third equation would be 0 equals 0 times Vz. That doesn't tell us that Vz is equal to 0. So essentially, Vz is unknown. Can't figure it out with the information we have. That's a crazy W. But anyway, I will see you next time.